So for the last talk of the session, we have Mitja Vodnik. He works on the LHCb online computing group as a firmware developer. His main task is the DAC backend firmware for the upgraded rich detector readout chain, and he's also one of the active maintainers of the Calibri HDL library. So go ahead.
Thank you for the introduction. Yeah, so today I will present you a piece of firmware that I have been working on for the past year that is meant for a packeted stream aggregation with time ordering. Okay, let's see. Okay. So, a bit of an overview. First, I will introduce you a bit to our experiment, the LHCb of CERN. And then for a bit of context, I will present one of the detectors, the rich Cherenkov detector and its readout, and the DIQ system that we have at LHCb. And this is to establish the context in which I'm developing this firmware. It's for the new readout ASIC, which will have a bit of a complex readout structure. And so my solution is called the Dynamic Derandomizing Buffer, which is the packet aggregation firmware that will handle this output. Okay, so first of all, a bit about CERN. So the LHCb detector is one of the four big detectors on LHCb. It's in a cavern underground. The front-end readout ASICs are located on the detector underground, and they're sending data over optical fibers to a data center that's on the surface. So that's where our data acquisition system works. So one concept we need to know about, but that Eduardo already explained very well, is there's two proton beams running around the LHC, and at the four big detectors, they collide, and each collision event we mark with a certain BXID. So that's how we identify each collision event. So on the surface, as I said, we have a data acquisition system. So underground, we have various detectors, and they are sending, they have hundreds of or thousands of readout ASICs that are sending data over around 11,000 optical links to our data center, where we have a lot of servers that are acquiring all the events and all the data and assembling it for each event. So this requires a fast speed network, and then all this data gets buffered and is used for event reconstruction. So the main point here is on the reception side in the data center, we have these readout boards that are based on Altera Area 10 FPGAs. So my specific problem is the readout of these two detectors, the Rich 1 and Rich 2 detectors, each requiring hundreds of readout ASICs to read out from single photon detectors. So the main part, or the data acquisition part of the rich detector, is the single photon detector, or a photomultiplier. These detectors are read out by the front-end ASICs, and then they are sent through CERN-developed radiation-hard protocol over optical fibers to the backend. So these ASICs will be upgraded in the following years to support the high precision timing that Eduardo was already talking about. So for this particular detector, we want around 10 picosecond precision. So yeah, we will get a new ASIC, which is called FastRICH, and it will come with several other complications. So because of the high pileup of the high lumi detector, it will use some a bit of a complicated readout format. So this is to optimize the bandwidth of the data lines. It will have 8 different packet types, varying size headers, varying size payloads. So this will already be a challenge to decode on the backend side. But the main challenge that I'm working with is that the time skew between the data arriving from multiple FastRICH ASICs is not constant or deterministic. And all the arriving packets have to be sorted at the backend side. So on this figure, you can see about like a simulated expected scenario, which is just a mess of packets arriving for different timestamps. So each color corresponds to a different event. So they will be mixed with random varying time delay. And my task here is fragment building. So each readout board needs to assemble all the arriving packets into one single packet that has all the data for a specific event. So the output of this fragment building has to be in time order or BXID order. And because of some extra complexities that this ASIC already introduces, we have about 30 to 40% of logic resources remaining to do this part. Okay. So the solution to this is a more generalized firmware, which will be able to be reused in similar scenarios. So we replace the BXID with a generic term called timestamp. So what we expect is just a lot of streams, packeted streams, with 2 sidebands. Describing the packet size in bytes and the timestamp. So we have an elementary sorting unit which sorts a power of 2 inputs into an ordered stream, so ordered in space and time. So the timestamps have to come out in order, and the data within the packet has to be in the order of the input index, let's say. So the idea is that we take this elementary unit and combine multiples of them into a tree structure which will aggregate the packets in multiple stages. So this is an example of it. So for example, in our FastRICH use case, we would get 168, so inputs from 168 different ASICs to the readout board, and then we aggregate it in multiple layers. So the first layer, for example, aggregates with 11 DDB units. It produces just 11 outputs, and those get fed into the next layer, which again reduces, aggregates them and reduces the number until we end up with a single output stream which should be ordered. So to accommodate for a random number of inputs, we also have carry units that just introduce some delay through a layer. That's to to save resources, basically, because to align with the streams that get through a sorting unit. So this tree structure is very configurable and very scalable. It's implemented as a recursion in VHDL, and the structure itself can be configured through a YAML file, and this is basically just fed as generics into the recursive design that generates this structure. So a bit about the ordering mechanism. So first of all, we have an arbiter that selects between the inputs. So we work with one input at a time. Then the writer writes it to a dual port RAM in the order as they arrive. So we will have scattered data inside the data buffer. We write the pointers to each input packets and their sizes to a separate dual port RAM. And also we aggregate the packet sizes into another RAM. So then the reading site, once we can consider each event timestamp complete, starts reading the RAM out of order so that we produce, so it just traverses the pointer table to produce an ordered packet stream. Okay, so the big problem here is when can we consider a timestamp completed? So when do we know that all the data for a certain event timestamp has already been saved into the memory and nothing new will arrive, so we can start reading it? So for that, I implemented an timestamp acceptance algorithm, which basically works with some sort of a timeout. So we define a maximum expected delay between, so a maximum expected skew actually between different input channels, so that once we receive a later packet, we can consider, okay, the packets that are a few timestamps behind can be considered complete, nothing else will arrive from them, and we can start reading them. And since timestamps are defined, well, they are a number of bits wide, so they have a limited range of values. They basically follow modular arithmetics. So I define this range on this on the total timestamp value range, and I consider everything outside of this range to be a late timestamp. So this range has a bit of an advanced acceptance area, which allows it to, for the new timestamps, to move this range forward. So how this looks like is we are receiving new timestamps. So the blue timestamps here represent active timestamps, but not yet completed. So at some point, we receive a timestamp that moves the acceptance range and leaves an already active timestamp outside of it. And now we can consider this one to be finished. We don't expect any more data for it. So we can signal to the read side to start reading all the data from this timestamp. And so this is how the range progresses. And then in case there is no new data arriving, at some point, or there are significant pauses between data arriving, we also need some timeout to automatically move the range before, so to basically start reading and accepting later timestamps as well. Okay, so this is the full architecture of the design. in more detail. So we have all the streams as arrays coming into the design. We have the acceptance range component with a timeout counter that defines which timestamps we're accepting. So there is a component that's rejecting any package that we consider late. Okay. Oh, sorry. Yeah. And so all the other components that I've already showed. So one good thing about this design is it's modular. A lot of the components used, like RAM readers, RAM components, the arbiter, the stream arbiter, they are all part of our Colibri library, which we'll present tomorrow in a tutorial. And since it's written in pure VHDL, with no vendor-specific cores included, this design is very portable. So we've built it. So since right now in LHCb we're using an Altera-based readout board, but in the future we plan to use an AMD-based one. We had to make it portable, and we did some resource estimations on 2 of the development boards. So we see that the resource consumption for these trees, for the sorting trees, goes linearly with the number of inputs. So for the AMD chips, these estimations are a bit preliminary because one of the RAM components is not yet optimized for it, and it produces a bit of a high RAM resources. So this will have to be worked on. So a bit about the verification during this. So most of the design, so most of the subcomponents that I've showed you have a formal verification test, and larger components, especially the ones handling data streams, have also UVVM-VVC-based test benches for to verify their behavior properly. And this is, on this project, I've tried to do test-driven development with formal verification. So to first define all the requirements for the design in a PSL file, and then start converting it to assertions and implement the features as I go. So this would be kind of the workflow. So add an assertion, the formal verification fails, implement the feature until it succeeds, and repeat until it's finished. So this can be a bit frustrating, but in the end, you get a very stable component that is already regression tested. And for the full design, I've written also UVVM-VVC test bench, which has a VVC component for each of the inputs, and we can feed the data to it from a file. So for example, for FastRICH, we would use Monte Carlo simulated data from the detector, so we get a very realistic scenario. The unit is a full sorting tree, and this is also being used to tune a bit the parameters of the acceptance range algorithm that I showed you. Okay, so as I said, the current status is subcomponents are tested, the tree is synthesizable, early version is already in hardware, so this is a lab setup which we have to test the FastRICH firmware, but so far it hasn't been really tested in the field. So for now it's more verified and tuned in the simulation. So to be done, as I said, the BRAM has to be optimized for AMD devices, and this design still has to be fully validated. And it's yet to be built also for the full data acquisition system of the LHCb. Okay, thank you very much for listening.
Hi, thanks. Very nice talk. Yeah, any questions up there? Yeah, you might have to come over to get a mic.
Hello. What is the importance of saving the data sorted in time if they come with the time of arrival information?
Sorry, what is the importance of sorting data in time? What we do here in LHCb is, okay, let's go here. So we do event building, right? So we get disordered data from different front ends, and we need to output it to the event builder network in order, because, well, the events then need to be built. Well, you have to sort it by event, right? And you get it scattered. You have to sort it so that you build each event fully. Does that make sense?
Any other questions? Yeah.
Oh, hi. Thank you for the nice talk. I have actually a few questions for you. Okay, so first of all, basically you rely for closing the frame, you rely on basically the timestamp of the FastRICH frame, right? And then you just have a time, let's call it a timeout, which is different with respect to what you define as timeout. But so that timeout is basically taken from simulation based on the highest occupancy cell of the RICH, right?
Yeah, so far, yes, so far I haven't worked with the proper FastRICH data.
Okay.
I have these tests that I generate with random data with different time skews. And yeah, the timeout it's usually the expected time between two events, okay, right? So in LHC, that's 40 nanoseconds. So the timeout would be one, well, the space between two bunches. Because that's when you expect a new timestamp.
Okay, great. Question 2 and 3. So do you have like a resource estimation on the Felix card for LPGBT plus Aurora decoder? Because my question is basically, do you have enough resources to implement these in the Felix?
Yes. So I don't have it here, but for example, here where I say that I have 30 to 40% logic left, it means until it's about 70 to 80% full. So the LPGBT, Aurora, and FastRICH decoding for 168 inputs, they use about 40% of logic. That's from my head, but okay. Paolo Durante made those
estimations. Okay, great.
Estimations. Yes.
Very last question, then I leave the floor to somebody else. How hard would it be to adapt this algorithm, for example, to data-driven front-end ASICs? So, for example, where this timestamp is in the data, and you don't have a bunch crossing rate you can rely on.
Sorry, I don't understand.
So, for example, I have TimePix4 in mind. You receive data on different links, and data are not ordered, but you don't have a bunch of data. You basically, each 64-bit word encodes its own time of arrival in the detector. Would
Okay,
this
but it has a
kind of-
timestamp.
Yeah, exactly. And my question is, have you ever thought to adapting this to a situation like that? Would it be feasible? So basically, there, each data its own frame, let's say.
Yes, like the size of the packet doesn't matter. So, I mean, but would you implement it in an ASIC or in an FPGA?
In FPGA.
Ah, yeah. Well, this is a very general firmware. It can be ported to any FPGA, yes.
Okay.
But I don't understand your problem, because...
Yeah, I'll talk
we
with
can
you
talk
later.
later.
Okay,
Yeah.
thank you.
Yeah, go ahead.
Hi.
Right, short question. Oh, somebody else? Sorry, go ahead.
So, hi, thanks for the very nice talk. I'm very happy to see you use PSL and formal verification on this one. About PSL and test-driven development, I guess you're one of the first to use that kind of development flow. Comparing that to using test benches to develop the module and then try to write the properties, that was a good idea to go with this TDD and formal at the beginning?
If it was a good idea?
Yeah.
That's what I'm asking myself, because it's it's a bit frustrating, yeah, because formal verification is very, how to say, it's not nice to you, yeah, so it's very good because it covers, it like spits out corner cases you don't think about, but that's also, it slows you down a lot with development, because sometimes you're a bit stuck solving something, you know, very, very weird, instead of just making a feature. But I don't know, in a sense, you would need to cover that corner case eventually. So maybe the initial investment is eventually worth it because you've already made sure your code works with all the weirdest corner cases. So, but I didn't compare. You know, it would be fun to compare one developer doing it with simulation and one with formal verification, what would happen. But yeah. It's definitely more straightforward to do test-driven development because each assertion literally corresponds to one feature. So it's very easy to do this flow. Whereas in a simulation, I don't see it so straightforward, maybe. Like a VVC basically covers the whole data stream. You can't really go step by step.
Thanks.
If that makes sense, yeah.
Any other questions?
Yeah, short one. Regarding the resources, have you considered using the UltraRAM for the virtual premium?
Sorry, I didn't catch that.
You were short on BRAM, but there's also the UltraRAM. Can you use that?
Ah, the UltraRAM.
Yes.
So I wasn't really short on it. Perhaps, as I said, it's not optimized for AMD, right? On ARIA 10, I guess UltraRAM is on AMD, right? It's not in ARIA 10, yeah. So for now, I'm targeting ARIA 10, and I'm OK with RAM there. For AMD, as I said, there's this component, the mixed with dual-port RAM with byte-enable writing and reading, which is not really supported. So I need to simplify that a little bit. And then I will see. Yeah, if I need to use a different RAM, then...
Is it using a single clock or dual clock?
This can use, so as you see, there's a synchronization stage through here, so it's dual clock.
Okay, then you cannot.
It can be also single clock,
okay.
but it's made to be flexible.
Any other questions? I might have one quick one, actually. So It sounds like you haven't decided which is the target board for this and the target FPGA, since you're trying out different possibilities. Do you know when that's going to be decided?
No, well, sorry. So they are both the target boards. Target boards. We have a target board that's the PCIe 40 that I showed with ARIA 10. And in the future, it's going to be the NetFelix.
OK, so it's going to be deployed in the final system with both of those?
Yes, that's for run 5 of LHC.
OK.
Yeah.
Thanks. If there's no other questions, then I think we've got a coffee break now. Do we stick to the timetable in Indico? OK, let's come back in 30 minutes, so at 25 past. OK, see you all after the coffee break.